trough is 10 feet long, and its ends have the shape of an isosceles triangle that are 3 feet across the top and have a height of 1 foot. Okay, so we've had one of these problems before, and it kind of goes like this. Okay, so this is the trough, and this guy's got 10 feet across, like that, and we know that it's, we said it was 3 feet across the top, so that's 3 feet, and then it said that it has a height of 1 foot. Okay, so we've got like a height of 1 foot. Okay, so what is the area of this thing? Now, what's really helpful to think of is when you have a general cross section here, like if something is sliced across, if it is a triangle, you can just calculate the area of the triangle and then just multiply by its length. Its length is like its extrusion, through space. So this guy, really, his volume is going to be 1/2 the base times height times the length. Okay, so times the length. All right, so 1/2 the base times the height times the length, and that's going to give us the full volume of this trough. Okay. Now, since I do know the length is actually 10. Okay, so I've got times 10, so that's 1/2 of 10 is 5, base times height. All right, now this trough is being filled with water at a rate of 12 cubic feet per minute, so it looks like we are given dH dt as 12 feet per minute, 12 cubic feet per minute. Okay, and how fast is the water level rising when the water is 6 inches deep? So how fast is the water level rising? That is a dH dt. Okay, and we are looking for it when the water is 6 inches. Now, if you do notice, this is in feet, so that did strike me when I saw inches there. So that's actually when the height is 0.5. Okay. Okay, so what this means then is I actually need to find a dH dt, but I have this b here. So what we've got to do is we've got to get a relationship from this triangle expressed in terms of h so that I can actually take the derivative. Now, I could take the derivative as it is, but if you notice though, the base is can be expressed in terms of h. So let's take a cross section here. Okay. So we know that's 1. We know that this is 3 all the way across. Okay. And if we were to fill it with water, okay, this is a 1-to-3 ratio. So no matter what, it's going to be 1-to-3. So this means then that the height is to the base the same as 1 is to 3. Okay, and if you can get this, that's fantastic, because now we can do the substitution just like we did in the previous problem. So we're going to set B equals 3H. Okay, so let's go back to this guy, and we can go ahead and sub that out. Okay, so notice that I didn't use 3 here for the base. I didn't use a 3. The reason why I didn't use the 3 is because that is not the water, like that. The water is not going to be, the water is only going to be 3 feet across if it is completely full. Okay, it is never exactly 3 feet across, but it is always 10 feet long. When I pour water in here, that is always going to be 10 feet. Like, even if I just pour in like 5 millimeters worth of water, that thing, it's going to spread out over that 10. So that's not going to change. So that's why we were able to do a sub. But the base, that's going to change. Okay, so that aside, we've got 5 times 3h, right? 3h times h. And so that gives us, the volume is 15h squared. So if I were to take the derivative, I get 30h times dh dt, and we sub what we know. We know that the volume is 12. So 12 cubic feet per minute, that is a 12, equals 30. We said h is a half, so that's going to be 1/2 a foot. Times dh dt. Okay, so then we're going to go, oh, did we square them? No, that is, yep, that's good. So let's go dh dt. So now we got 12 divided by 15. Okay, which equals 4 over 5, and that's going to be feet per minute. Okay. I'll be right there in a minute, Laura. Function f is twice differentiable here. Okay, so we're all at 3. Here's the, not the derivative, first derivative, second derivative. What is the value of the approximation at 2.9, and then using the line tangent to the graph there. It does not ask to give an over or an estimation, so that's okay. So I'm not sure what the second derivative is used for, other than showing whether or not it would be an over or an underestimate. Okay, so let's go ahead and find the approximation at 2.9. Let's get this first. So we said that the point, when I plug in a 3, I get 2. The derivative at 3 is the slope. Okay, so this means that capital L, the line equals the derivative, and then we've got x minus 3, and then plus 2. Okay, or in some textbooks would put the 2 in front and then x there, but that's fine. And this is the line that approximates what this function is. So we want to go ahead and plug in a 2.9 there. Okay, so 2.9 minus 3 plus 2. So this is the stuff that you can kind of do in, the idea here is that this is something that you can do in your head. So this would be 0.1, negative 0.1 plus 2. So what this is saying then is that we actually are going to take, that's a negative 0.4 plus 2. And so that means we are going to go down a little bit. So we're going to be at 1.6 is the estimate of this guy based on this information. Okay? All right. Now, because this is negative, that means that we do have a concave down, which means if we drew a line over there, this would be actually an overestimation. Okay, but that's not what they asked, so we don't